Okay, so we're gonna continue with our discussion on the packed tower for absorption and distributing. So I think in our last lecture we have covered most contents on this topic. So in today's lecture we're gonna finish up on this lecture, then we can move on to distillation. Okay. So recall for the packed tower, we basically talk about in a packed tower, we have a liquid stream coming down, we have a vapor stream going up, right? And we talk about for packed tower, we use a concept that's called HETP, height equivalent of a theoretical plate, to basically analyze it, right? And in that case, we assume a certain height of a packed region is equivalent to a trade tower. Okay, and to figure out what's the required height to be equivalent to a tree in equilibrium, and we have to consider the mass transfer between the gas phase and the liquid phase. Okay, and we reviewed briefly the two-film theory, which is a theory we use to analyze the mass transfer between the gas phase and the vapor phase, right? The gas phase and the liquid phase. So recall in a two-film theory, we basically have four compositions, right? We have two composition for the gas phase, right? One denotes the bulk composition, the other denotes the interface composition. We also need to have two compositions to denote the liquid phase composition. So, and we know at interface, the vapor is in equilibrium with the liquid. So we can basically correlate the vapor phase composition with the liquid phase composition at interface using equilibrium, right? If you know the K value, you can relate them. And for the bulk composition, we can basically relate them by looking at the mole balance of the whole system, right? That will give us operating line. So let's take a look at how we do that. Okay. So here, this is a figure, a schematic of a absorption tower, right? Pack tower, and let's draw a control volume that's encapsulating the top section and a ans plate, well, not ans plate, like a distance L from the top of the pack tower, right? So in this control volume, we have two streams coming in. That's the liquid absorbance. Then we have the vapor going up. We also have two streams leaving this control volume. We have the liquid coming down, leaving this control volume. We also have the vapor leaving the tower. Okay, so basically we can write down the mass but mole balance equation for this control volume. Now here, different from the trade tower scenario, in which we use mole ratios, and that's mole ratio. That's basically capital case X and Y, right? We also use the solid free fluoride, that's L prime and V prime. So here we use the mole fraction, right? That's lowercase x and y, and the total fluoride, right? That's L and V without prime, right? So then we can write down the solute mole balance, right? So we have X in minus L multiplied by L in, that's the solute coming to the tower. We have Y multiplied by VL, that's the solute going to the control volume carried by the upcoming vapors. Okay, that's gonna be equal to the solute leaving the control volume, right? This is the solute leaving the control volume carried by the downcoming liquid stream. And also this is the solute leaving the control volume carried by the exceeding vapor phase. Okay, so here X and Y refers to the mole ratios, mole fraction of the solute in the liquid phase and the vapor phase respectively. And L and V refers to the total flow rate of the liquid and the vapor phase, respectively. Okay. Now, here we need to, we can make an assumption that if for dilute solutions, then basically V and L are approximately constant, right? That means we know that as the liquid absorbance coming down, basically it's gonna absorb the solute from the upcoming gas phase, right? So the total flow rate of the liquid stream will actually increase. But if we assume a dilute solution, that means the amount of solute, is kind of negligible or very small compared to the amount of your liquid absorbance or your carrier gas, right? In this case, we can assume the V and L, the change of V and L is small, so they are approximately constant, right? That will help us to derive this equation here, right? So basically, you can, in that case, for dilute solution, V and L are constant. We can drop the subscripts for L and V, right? Then we can take all the Y terms to the left. We take all the X terms to the right, right? Then we have Y minus Y out on the left, and then we have X minus X in on the right. Then you can divide V on both sides. Then you will have basically Y minus Y out equals L over V multiplied by L divided by V, right? Then you can just move Y out from left to right. You get this equation, right? So that gives you the packed absorber operating line that relates basically the gas phase composition with your liquid phase composition. Okay, and we can draw this on a y-axis diagram, and the slope of this straight line is gonna be the ratio between the liquid flow rate and the vapor flow rate, right? And we know Y out and X in. So similarly, you can do an analysis for a stripping tower. Here, instead of, we're gonna encapsulating basically the bottom of the tower and a distance from the L from the bottom of this tower, right? And similarly, write down the solid mole balance equation, right? So you have this is what's coming in plus in the liquid, what's coming in from the gas phase equals what's going out in the liquid and vapor phase. And again, for dilute solutions, V and L are constants. Then you can just move all X, Y terms to the left, X terms to the right, divide V on both sides, then you can get this equation, right? Again, which is also a linear equation that relates the Y with X. You can plot it on a XY diagram. So here, XY are bulk composition, right, instead of interface composition. Okay, so that gave us the last piece of the puzzle. With that, we can go to look at the overall graphs, which has the operating line, equilibrium line, and all the important mass transfer line, and all the important information for us to analyze a packed tower, right? That's so here, remember that when we derive this, basically this operating line and equilibrium line, we made a few assumptions, right? For the operating line, in order for it to be a straight line, right? In order to derive it, L and V needs to be constant, and that is dependent. That is basically derived based on the assumption that we have dilute solutions. So we have X, Y are small. Okay, then here the equilibrium curve is a straight line. That means K, the slope of this line, which is the K value, is a constant, right? And in this case, only when temperature and pressure are constant and an ideal system, we can get that conclusion. Okay. So now let's relate everything together, right? Let's move on. We've talked about this. Also talk about these. Yeah, so now let's just connect everything together. We can connect the operating line, equilibrium line, and the mass transfer on the same figure, right? So to understand it, let's look at some of the points and the lines on this graph, right? We already talked about the blue line. Blue line is operating line, and the red line is equilibrium line. Okay, so there are a couple points on this figure. What do A, B, C, D mean? Okay, A sits on the operating line. That basically means the bulk composition of the gas and the liquid phase, right? At any location in a packed tower. Then B, C, and D, they sit on the equilibrium line, right? So which means the composition, this should satisfy basically the equilibrium constraint. And B point refers to the composition, gas and the liquid phase composition at the interface, right? So they are in equilibrium with each other. So that's basically Y and Xi here. Then point C has the same Y value as point A, right? But the X value here is basically in equilibrium with Y value, right? Because it's sitting on this equilibrium line, right? So Y is a bulk gas phase composition. So the X is in equilibrium with Y. That means it's the fictitious liquid phase composition that is in equilibrium with your bulk gas, right? Similarly, point D has the same X coordinate with point A. So the Y star is in equilibrium with X, okay? So that means Y star is the fictitious gas phase composition that's in equilibrium with X, right? Remember here, on the right of this line, we have the liquid phase. So we use X to denote its composition. So Y really doesn't, the concept of Y doesn't apply on this side because Y refers to the gas phase composition, right? So that's why we say it's a fictitious gas phase composition because we get Y star by applying the equilibrium constraint. So Y star equals key value multiplied by X, right? So it's a fictitious gas phase composition that's in equilibrium with X, okay? So what are the four segments, line segments, AE, AF, AD, and AC, okay? So AE is on this vertical line, so they have the same X coordinate. The length of AE is basically Y minus Y subscript YI, okay? So that basically gave us the mole fraction difference in the gas phase. So that's a mass transfer driving force in the gas phase. Similarly, AF is the length of AF equals X minus XI. So that's a liquid phase mass transfer driving force. Okay. AD is Y minus Y star. That's the overall mass transfer driving force, right? Driving force across both the gas phase and the liquid phase when you use the overall mass transfer coefficient based on the gas phase composition. Okay. And AC equals X star minus X. That is the overall mass transfer driving force across both the liquid and the gas phase if you use a liquid phase overall mass transfer coefficients. Okay, so here when you use X minus X star as a driving force, the overall mass transfer coefficient will be different from when you use Y minus Y star as the driving force, okay? So the last line is AB. What is AB? Now, A is the bulk composition and B is the interface composition, right? And we previously have derived basically these two points will sit on this curve, right? And we derive this curve by basically letting the mass transfer flux in the gas phase to be equal to the mass transfer flux in the gas phase, right? Gas phase to be equal to the liquid phase. So basically, it is the mass transfer line. Okay, great. So then now we have a very good understanding, so we can, figure out by reading this figure, we can get a lot of information to analyze the pack tower case. Okay, so then we're done with the pack tower. Next topic, we're going to move on to the distillation.